All right, welcome to the Explainer. Today we're going to talk about something fundamental, the very building blocks of all computing. We're putting the classic bit, the foundation of our entire digital world, right up against the revolutionary qubit, the heart of what's coming next in the quantum future.
So here's the game plan. First up, we'll get a solid handle on the reigning champ, the bit. Then we'll introduce its pretty mysterious challenger, the qubit. After that, we'll compare their rules, their power, and finally, we'll look ahead to see what their shared future might actually hold.
Okay, so let's just jump right in. We're going to start with the absolute foundation of, everything digital, the humble but incredibly mighty bit.
At its heart, a bit is just beautifully simple. Think of it exactly like a light switch. It can only be in one of two states, definitely off, which we call 0, or definitely on, which we call 1. And that's it. There's no gray area, no in-between whatsoever.
And that simplicity, that's its superpower. I mean, this isn't just an abstract idea, right? In the real world, it's a tiny electrical charge, either high or low voltage. You've got billions, literally billions, of these super stable switches working together to run everything from your phone to the entire internet. The key word here, the most important thing to remember, is reliability. But what if we decided to ask a really, really weird question? What if we could just break that fundamental rule? That one question, that single idea, it completely challenges a century of computing and just blows the door wide open to a brand new way of thinking.
Which leads us straight into the strange, kind of counterintuitive and unbelievably powerful world of the qubit, the fundamental piece of quantum computing.
So unlike that simple on-off switch we just talked about, a qubit plays by a whole different set of rules, the mind-bending rules of quantum mechanics. It doesn't have to pick a side. It doesn't have to be a 0 or a 1. It can actually be in a combination of both states at the exact same time. And this amazing property, this is what we call superposition.
So you can almost think of the qubit state like a recipe. It's not just a 0 or a 1. It's more like a certain percentage of 0 mixed with a certain percentage of 1. It holds both possibilities at once.
Okay, this right here, this is probably the absolute best way to picture the difference. A bit is that click-clack digital light switch. It's either on or off. A qubit, that's a smooth analog dimmer dial. It can be all the way off, all the way on, or, and this is the key part, it can be any shade of brightness in between, holding this whole spectrum of possibilities.
And this is where things get really, really weird. See, a qubit lives in this fluid, hazy state of potential, but the very second you try to look at it, the moment you measure it, bam! It's forced to pick a side. It collapses into either a definite 0 or a definite 1. The very act of observing it destroys that superposition. The quantum magic just vanishes.
So yeah, as you can probably guess, when you have such wildly different building blocks, it means these two types of computers are playing completely different games, with completely different rule books. Think about it like this. A classical computer is a step-by-step worker. It solves problems one calculation at a time, in a sequence. But a quantum computer, it gets to use that superposition magic to explore every single possible solution all at once. Because just a handful of qubits can represent this ridiculously huge number of states simultaneously, they can basically check out all the possible answers in one go.
Right, and this fundamental difference in how they operate leads to a massive difference in what they're actually good for, and, just as important, where they fall short. The takeaway here is that classical computers, the ones built on bits, are honestly the perfect tool for like 99% of everything we do. Databases, websites, the apps on your phone, they're masters at that stuff. They only start to struggle when you throw problems at them where the complexity just explodes exponentially. Qubits, on the other hand, are like these highly specialized, but kind of temperamental geniuses. Yeah, they have the potential to crack some of those impossible problems. We're talking things like breaking modern encryption at speeds that are just unthinkable for a classical computer. But here's the catch. They are incredibly fragile. The slightest little disturbance, a change in temperature, and they lose their quantum state. They need to be kept super cold, and they're really prone to errors. All right, so let's put them side by side, a direct head-to-head comparison to really nail down the differences.
What really jumps out from this table is that huge contrast in stability and where they're at today. The bit, based on regular old classical physics, is rock solid, mature, and it's literally everywhere. The qubit, running on quantum mechanics, is super delicate, it's still experimental, and for the most part, it's living in research labs.
So this really sums it all up perfectly. The bit? That's your dependable workhorse. It can do pretty much anything, and it does it reliably. The qubit? That's your thoroughbred racehorse. It's not for everyday tasks, but on a very specific, very difficult track, nothing can beat it.
So if it's not a competition, if the qubit isn't going to replace the bit, then what does the future of computing actually look like? Is it one or the other?
Well, the future isn't a battle. It's actually a partnership. It's a team-up. What we're really looking at is a hybrid future. The powerful classical computers we have today will still be running the show, but think of them as the orchestra conductor. When they hit a problem that's just impossibly hard, they'll hand it off to a specialized quantum processor to find the answer.
And that, of course, leaves us with the most exciting question of all. I mean, think about it. Designing new medicines, creating new materials atom by atom, completely revolutionizing AI, solving global-scale logistical problems. Which of today's truly unsolvable problems will this powerful new team finally crack? We're just starting to see what's possible.